matrices on a 2n by 2n and two copies of an arbitrary n by n alternating sign matrix, and you put those together and it gives you the number of quarter turn symmetric.
So there is a proof, but not the next one.
There is a proof.
Yeah, not the next.
Yeah. But not one, it's a verification proof. It doesn't really explain why this has the nice structure that you see there. And Greg Cooperburg was using the machinery that had been developed from statistical mechanics. So he was working with a 6-vertex model, and not too surprisingly, he found some generalizations of alternating sign matrices. This is one of the more esoteric ones. What you do is, instead of having, well, you've got your in edges on the left and your out edges on the bottom, but at the top you loop around instead of heading off. And also on the right side you loop around instead of heading off. And you're again looking at filling this with 6-vertex models. Greg called these UU, alternating sign matrices. Effectively what you're doing is you travel up and around, and the entries that you hit have got to sum up to 1 as you make a U-turn through your matrix. And they've got to alternate in sign. So here we've got our 1, minus 1, plus 1. Here we've got our 1, minus 1, plus 1. And the same thing has to happen as you make a U-turn horizontally. That they've got to alternate in sign and add up to 1. And he proved this formula for counting the number of UU alternating sign matrices. So there are things that can be done along those lines. Soichi Okada, 2004, was able to extend some of Greg Cooperburg's work, again using the 6-vertex model as the basis and using triangle-to-triangle relation as the key insight. But one of the nice things about Okada's paper is that he's able to cast these in terms of dimensions of irreducible representations. And in particular, we're looking at the irreducible representation of GL2n indexed simply by this partition, which has 2 copies of n-1, 2 copies of n-2, all the way down to 2 copies of 0. So it's a nice staircase shape. And the number of alternating sign matrices is essentially the Shor function of that particular, well, it's the dimension of that particular representation. And Okada also managed to prove a couple of additional identities. In particular, he was able to prove Robin's conjecture for the number of alternating sign matrices that are both vertically and horizontally symmetric. So VH are vertically and horizontally symmetric, and in the case of vertically and horizontally symmetric 4n plus 1 plus 4n plus 1 alternating sign matrices, he again expressed this in terms of a dimension. It's a cross product of the symplectic group and a special orthogonal group. With these particular sets of parameters. So Okada proved the formula for 4n plus 1 and also for vertically and horizontally symmetric 4n minus 1 by 4n minus 1. More recently, physicists Razumov and Stroganoff proved the conjectured formula for quarter-turn alternating sign matrices. If you'll recall, Greg Cooperburg proved this in the case of 4n by 4n. Razumov and Stroganoff also proved the formulas in the case of 4n plus 1 by 4n plus 1 and 4n minus 1 by 4n minus 1. You cannot get, this is a nice simple exercise, you cannot get a quarter-turn symmetric alternating sign matrix if the dimension is congruent to 2 mod 4. So it has to be plus or minus 1 or 0 mod 4 in order to get quarter-turn symmetric. but the formulas are very similar.
There is a formula, it's equal to 0.
Well, yes, okay. For counting the symmetry classes of alternating sign matrices, there's now only one unproven formula. There's several symmetries that you can think of and that Dave Robbins did come up with where he looked, and it did not appear that there was a nice formula in terms of factorials. There's certain classes of symmetries that just don't seem to give anything nice. But all of those that do seem to give something nice have been proven, except for this one. These are alternating sign matrices that are symmetric across both diagonals. And it's been conjectured that this is the formula. At this point, it's almost certainly true, but nobody knows how to prove it. I want to move on next to fully packed loop configurations, which is a place where the physicists, again, have expressed a great deal of interest. This is something that they had studied before the work on alternating sign matrices was connected to work in physics, but there's been a lot of interest in this since then. One of the things that you can do is to take each of these vertices and alternately label them as either an in vertex or an out vertex. So this is in, this is out, this is in. If this is in, this is out, and this is in, so that they alternate in and out. And you begin to connect these edges. So if you're at an in vertex, you connect the two in edges. If you're at an out vertex, you connect the two out edges. So you do this, and so what you wind up with is a path through this directed graph. And if we do it at every single one of these vertices, notice that I have taken out, since I'm connecting the out edges here, I haven't bothered to write in the in edge here. But what you're going to get is a collection of paths that are non-crossing through this directed graph and that hit every single vertex. So we're looking at what is called a fully packed loop configuration, which is simply a collection of paths that are non-crossing and hit every vertex. In this particular case, every path starts on an outside edge, and of course then must wind up on an outside edge. You can get a loop configuration that actually has loops within it. But we have a nice one-to-one correspondence between these fully packed loop configurations and the alternating sign matrices. If you've got the alternating sign matrix, that uniquely determines the loop configuration. And if you've decided in advance which are the in vertices and which are the out vertices, if you know what the paths are, then that determines which are in and which are out arrows at each vertex, so that uniquely determines the alternating sign matrix. So there's a simple one-to-one correspondence between alternating sign matrices and fully packed loop configurations. And one of the things that you can do with these, if you go ahead and label the edges, this gives you a pairing on the edges. So if we put the labels in this case, it's a 5 by 5 alternating sign matrices. We label 1 through 10. This is an alternating sign matrix or a fully packed loop configuration that does a non-crossing pairing of these outside vertices, 1 with 2, 3 with 10, 4 with 5, and so on. And a natural question to ask is, given a pairing, how many different alternating sign matrices correspond to that pairing? One nice result that's not terribly deep is that if you take the pairing that pairs adjacent outside edges, the number of alternating sign matrices, of n by n alternating sign matrices that correspond to that pairing is just the number of alternating sign matrices of one smaller size. So you can get those as a subclass. But the more remarkable observation that was made and proven in 2000 is that